Before we get started on today's stuff, do you have any questions about anything from last week? Okay. Today we get to talk about section 8.3. Good times. And 8.3 are complex numbers in trigonometric notation, which is kind of weird. So complex numbers, as a reminder, those are numbers that we write in the form a plus bi, where a is the real portion and bi is the imaginary portion. And we can write any number in this complex number system. We could write the number 3, for example, as 3 plus 0i. We could write 5i in here. It would be 0 plus 5i, and so on. And so what we need to do now is do something that I told you we couldn't do, and I tell all my algebra students we can't do it. We're going to graph imaginary numbers. We're going to call this our normal x-axis our real axis, and we are going to call the normal y-axis our imaginary axis. And so if I were to graph, say, the point 3 plus 2i, I'd come over 3 on the real, up 2 on the imaginary, and that's the point 3 plus 2i. The point 2 minus 4i would be 2 on the real, down 4 on the imaginary, so that'd be 2 minus 4i. So you can see we can plot these. We did have to say, okay, well, I'm going to call the x-axis my real axis and the y-axis my imaginary, but now we can plot all of these points. Negative 2 plus 3i would be up here, and so on. All right, so now what we need to do is say, look at the absolute value of a plus bi. Write that down in case somebody looking later doesn't recognize the symbol for some reason. The absolute value is the square root of the sum of the squares of the coefficients. So we could calculate, say, the absolute value of 3 plus 2i. That first point I graphed would be the square root of 3 squared plus 2 squared, which would be the square root of 9 plus 4, which would be the square root of 13. That's the absolute value of 3 plus 2i. You will be asked to find the absolute value of some of these complex numbers, and that's all you need to do. Notice the I we just kind of ignored because, well, we're squaring I, which would give us a negative, but you don't even worry about that. You just look at those coefficients A and B. That gives you that absolute value. So that's a little, just kind of an aside there, a little bit in the background, but one of the things that we're going to look at now is how to get a complex number in trigonometric notation. Oh, so what I want to do is, again, I'm just going to look in the first quadrant. At this point, a plus bi. I could drop a perpendicular. We would call this r, because notice that point, we've got a radius here like we've talked about before, and that could make a circle. The a is the real part, so that would be this portion of our triangle. The b is the imaginary part, so that would be that portion. We've got our angle here, theta. And so I could say that cosine theta is adjacent over hypotenuse. I could say that sine of theta is opposite over hypotenuse, which means I could multiply both sides by r and so on. A would equal r cosine theta, and B would equal r sine theta. And I'm going to take advantage of those relationships here to convert a complex number to trigonometric notation. So if I've got a plus bi and a equals r cosine theta, and b equals r sine theta, I've got the format here. I see r shows up in both of those, so I could conceivably factor that out. And get our trigonometric notation for these complex numbers. Now, one of the things that they often do, just so that we don't make as many mistakes, is they'll bring the I in front of the r sine theta. It's just so we don't accidentally confuse the I with the angle. So this is the format you're likely to see most often. Now, how do I use that? Let's take a look at.
Question: Wouldn't that be r squared? Yeah, yeah. He's asking the.
It would not be. Oh, this r shouldn't be there. Sorry. Let me erase that. See if I can. Those r's should be there. Sorry about that. Because I factored r out, right? So it should be r times cosine theta plus sine theta I, or cosine theta plus I sine theta. It shouldn't be an r squared. Thanks for pointing that out. Must be a Monday. Maybe I can blame it on Corona. I don't know. Let's see. So I've got, say, 1 plus I. And I need to take this over into my trigonometric notation. So let's take a quick look at where 1 plus I would be on here. One real, one imaginary. So that's right there. So I've got some angle here. Now, which angle has the same x and the same y? Such that this is 1, this is 1. This ought to look kind of familiar. We did Pythagorean theorem. That
root 2.
So 1 root 2.
That's a 45-degree angle.
It is. All right, so that helps us out an awful lot here. R is root 2 cosine 45 degrees plus I sine 45 degrees. That's the same thing as 1 plus I. Or, if we needed it in radians, cosine of pi over 4 plus I sine pi over 4. Those are identical as far as this is concerned. So now we've converted a complex number over to trigonometric notation. Now that was an angle we recognized. We won't always get that, but sometimes we do. Do we have any questions on that before I move on to another? All right, let's try another one. If I've got enough space under here. Not really. So let me get a new one. All right, let's look at root 3 minus I. So come over here, root 3, which is about 1.7. Drop 1. This is root 3 minus I. So drop my perpendicular. This is 1. So I need R. Well, Pythagorean theorem, R would equal the square root of root 3 squared plus 1 squared. Square root of 3 times the square root of 3 is 3. 1 squared is 1. So this is the square root of 4. So this must be 2. Now we knew that from our earlier triangle work where we have a 1, 2, root 3. But that also tells us what angle we've got here. That would be 30 degrees. That gives us our 1, 2, root 3. So what do we have here? We need R, which is 2, times cosine of theta. Now we said it was 30 degrees down. This is fourth quadrant, where our angles are between 270 and 360. 360 minus 30 is 330 degrees, plus I sine 330, or we were in radians. 330 is the same as 11 pi over 6. We do have to make sure that we're not using the 30. That was just a reference angle. The actual angle itself started here and rotated all the way around to there. That's our 330. If I had just put 30, it would have put me up here in the first quadrant. So I do need to make sure I use the actual angle and not just the reference angle when I'm typing into this format. But it does work pretty well to do it that way.
So this chapter just consists of converting it over like this. We're not trying to solve it completely, or
Right now, we're just converting to another format.
okay.
We will be doing some math with this, but first we need to be good with transferring back and forth between the two. So now actually let's convert over to standard notation, which is the a plus bi. I've got, let me kind of separate this out, give myself a little bit of space here. I've got 2 cosine 120 plus I sine 120 and I need to take that over to standard notation a plus bi. So I need to figure what a and b are. But we know that a is r cosine theta, right? That, oh, let me get a different color. This gives me a, and that gives me b. So this is the r. Here's cosine theta, so I've got 2, oh, sorry about that, 2 cosine 120. Well, the cosine of 120 is negative 1/2. 2 times negative 1/2 is negative 1. So that's a. B is r sine theta, which is 2 sine 120. The sine of 120 from my unit circle is root 3 over 2. And 2 times root 3 over 2 is root 3. So now I can plug those in. A is negative 1. B is root 3. And then I've got my I. So that would be standard notation, or 2 times the quantity cosine 120 degrees plus I sine 120 degrees. So we can convert back and forth from trigonometric notation to standard and vice versa. Do we have any questions on that? I'll do another one here with radians. Myself a little more space here. Root 8 times cosine of 7 pi over 4 plus I sine 7 pi over 4. And I need to convert that to standard notation, a plus bi. So once again, a is r cosine theta. So that's root 8 cosine of 7 pi over 4. 7 pi over 4, based on what I see on my unit circle, the cosine is root 2 over 2. And the square root of 8 times the square root of 2 is the square root of 16. So that's 4/2 or 2. B is r sine theta. R is still root 8. The sine of 7 pi over 4 is negative root 2 over 2. So that gives me negative root 16 over 2, which is negative 2. So A is 2, B is negative 2. So that's standard notation for square root of 8 times cosine of 7 pi over 4 plus I sine 7 pi over 4. So now we've gone back and forth. We've gone from standard to trigonometric and from trigonometric back to standard. Have you any questions about those at all?
I have a question. Will the homework only be dealing with the unit circle? Meaning like angles from all of that, we have on the unit circle, or is it gonna throw like completely random angles also?
If I remember correctly, this is strictly from unit circle angles. I don't recall them giving anything that's not on the unit circle in this section. I should double check that, but I'm pretty sure that's the case.
All right, thank you.
You're welcome. Okay. So now what they've got us doing is they've introduced us to a couple of formulas here. We've already added and subtracted complex numbers in algebra where you add the real portion and you add the imaginary portion, something like this. 3 plus 2i plus 2 plus 3i. I should probably not do 3. I should probably do a 2i here so it stands out a little better. So we add the real portion, 3 plus 2 is 5. And then you add the imaginary portion, 2i plus 2i is 4i. And if this had been a negative 2i, then the imaginaries would have disappeared and so on. So that should just be some review right there. If we are dealing in trigonometric notation, when we multiply, like if we did 3 plus 2i times 2 plus 2i, we FOILed it, such that we got 3 times 2 is 6, plus 6i, plus 4i, and then we had plus 4i squared. Recall that I squared is negative 1, so this becomes negative 4, which gives us 2 plus 10i. That would be the product of those two. In trigonometric notation, it's a little different. We've got r1 times cosine theta 1 plus I sine theta 1. And we are going to multiply that by r2, not d2, but cosine theta 2 plus I sine theta 2. Now, if we're multiplying those together, it's slightly different in that the result is r1, r2. So you multiply those together times cosine of theta 1 plus theta 2. So you add the angles inside here. So it's slightly different there. I'm sure if we distributed the r's and then FOILed and did everything, we could come up with the same thing, but the reality is it's faster just to use this one formula. And it's similar when we do division. r1 cosine theta 1 plus I sine theta 1 divided by r2 cosine theta 2 plus I sine theta 2. We're going to go ahead and divide the r1 by r2. multiply that by the cosine, and now we're going to take the difference. Theta 1 minus theta 2 plus I sine theta 1 minus theta 2. So they're similar. Those are just formulas that we need to learn and practice using. So that was really introduction to those formulas. Now I'll go ahead and work a problem out and show you how it works so that you can see that. But I wanted to give you time to write those down. Those are on page 582 and 583 in your text. If you want to refer back to those. But let's work one out and see it in practice. See if I can leave that on there. Now, with this problem, I'm told to divide 2 cosine of 3 pi over 2 plus I sine 3 pi over 2 by 4 cosine pi over 2 plus I sine pi over 2. Okay, so I'll use this division formula we just had. So I'll go ahead and write it out. Probably already got this solved in the time it's taking me to write this out. So we divide the numerators r by the denominators r, by that by cosine 3 pi over 2 minus pi over 2 plus I sine 3 pi over 2 minus pi over 2. So we've got 1/2 cosine of 2 pi over 2, which is pi, plus I sine of pi. And we know what the cosine of pi and the sine of pi are. Cosine of pi is -1. Sine of pi is 0. So I'm left with 1/2 times -1 plus 0i, which is -1/2. So dividing 2 cosine 3 pi over 2 plus I sine 3 pi over 2 by 4 cosine pi over 2 plus I sine pi over 2 is -1/2. Sometimes it works out easier to do this method than just to worry about the standard notation. Let's see, what would this have been? 3 pi over 2 is basically the negative y-axis. So we would have had 0 minus 2i would have been our standard form for this first one. Pi over 2 is the positive y-axis. So 0 plus 4i. We would have had -2i divided by 4i. And that would work out pretty well. Yeah, any questions on that? I'll work some more.
So that -1/2, if we were to graph it, what would that, so never mind. Actually, I answered my own question. Sorry. Thank you.
Let me work another one. These were both on the y-axis, so it probably would have been just fine to divide it in standard notation. I consider a problem that is in standard notation. Oh, turn my pen around. Say 1 plus I divided by 1 minus I. Just thinking about how that might work. See, I might be able to multiply by the conjugate and mix things up a bit, or I can convert these to trigonometric notation. Thinking about what we've got here. 1 plus I would be up here. 1 minus I would be down here. In both cases, this is a 1, that's a 1, this is -1. In both cases, these are 45 degrees. And so this would be √2. This would be √2, just thinking about how we would get there using Pythagorean theorem and whatnot. So I would have √2 times cosine of 45 degrees plus I sine 45 degrees would be my numerator. The denominator would be √2 cosine 315 plus I sine 315. And so we would have √2 divided by √2, which is awful nice, times the cosine of 45 minus 315 plus I sine 45 minus 315. That should have probably been brackets. So √2 over √2 is clearly 1. So we're left with just cosine of negative, what do we have there? -270. I subtracted that right. Plus I sine -270. Those are degrees. -270, starting here and rotating through -270, that brings me up to right there, which I often think of as 90 degrees. Cosine of -270 is 0. Sine of -270 is 1. And 0 plus 1i is just I. That would be the quotient of 1 plus I over 1 minus I. And they specifically said to convert to trigonometric notation and then use the formula. But this one is probably easier this way than simplifying other. Any questions on that one? Got a couple more theorems to look at. Those are powers of complex numbers and roots of complex numbers. And then that would wrap up our section here. think we've got enough time to do both of those without a problem. Let me show you de Moivre's theorem. Kind of a weird name. I shouldn't make fun. This is the first one's a V and the second one's an R, de Moivre's theorem. And this is for dealing with powers. So we've got our R cosine theta plus I sine theta. What if we needed to raise that to some power? We've dealt with, in algebra, complex numbers raised to a power. Well, in trigonometric form, Moivre said that we just need to raise r to the n power. And it turns out we're going to multiply that power by theta. So n shows up a couple of places. N will be the exponent on the r value, and each of our angles will be multiplied by n. So to see this in action, let's raise say 1 plus I to the 9th power. Now, in chapter 11 of the book, we learned binomial theorem, which would allow us to expand this just fine. We're not going to talk about that in this section. That was covered in Math 143. But let's go ahead and convert. We've already done the 1 plus I a couple of times, actually. That became radical 2 cosine of 45 degrees plus I sine 45. Now let's raise that whole thing to the 9th power. As a reminder, another way to write square root of 2 is 2 to the 1/2 power. Sometimes it's easier if we raise that to a power like that to see what we're doing, because the square root of 2 to the 9th power now becomes 2 to the 9/2. Notice r to the 9th. So square root of 2 to the 9th would be 2 to the 1/2 to the 9th power, and you multiply exponents. 9 times 1/2 is 9/2. Now we've got cosine of 9 times 45 plus I sine of 9 times 45. 9 times 45 is 405. And thinking about coterminal angles, choose this 405 minus 360 is 45. So just thinking about coterminal angles can make this a little easier. So 2 to the 9/2 power. Oh, let's see, we simplify that down and so on. It comes out to be 16 root 2. And then cosine of 45 plus I sine 45 we know the cosine and sine of 45, those are both root 2 over 2. I'm going to want a little more room here if I can get it. So 16 root 2 times root 2 over 2 plus root 2 over I root 2 over 2, I should say. Root 2 times root 2 is 2. 2 times 16 is 32. Well, that looks like 16 plus 16i. That would be 1 plus I to the 9th power. Now, I did a couple of different things here. I played around with the radical, converted square root of 2 to 2 to the 1/2 power so that I could get 2 to the 9/2. I also looked at coterminal angles to simplify that as much as I could. We know that coterminal angles have the exact same sines, cosines, and tangents. So I can treat it that way. And then there was a little bit of algebra there. You got any questions on that one? Let me show you the roots. I've only got, and time's still flying in this class. I've only got about 7 minutes left. So let me show you the formula, and we'll talk about how that works when we're taking roots of a complex number. So we've got our complex number. And I am going to take that to the nth root, so 1 over n. That's kind of like the 3rd root or the 4th root, the 5th root. Those numbers I'm saying would take up the n. And this is kind of weird, so I want to make sure I mention this. You go ahead and take that nth root of r, and this is where it gets really weird. Cosine of theta over n plus k times 360 over n. I'm going to talk about what k is and how this works, plus I sine of the same thing. And I'll hopefully have time to get one of these in. K is 0, 1, 2, all the way up to n minus 1. So if we're taking the 3rd root, n is 3, then we'll go all the way up to 3 minus 1, which is 2. So we would only have those 3 if n equals 3. But let's see this in action. Let's find the square root of 2 plus 2 root 3i. Okay, so this 2 plus 2 root 3, it's up here somewhere because it's positive a, positive b. So this would be the real, this is the imaginary. So the square root of the sum of the squares, 2 squared plus 2 root 3 squared, and I'm taking the square root of all of that. 2 squared is 4. 2 root 3 squared, you've got the 2 times 2, which is 4. Root 3 times root 3 is 3. 3 times 4 is 12. And I need the square root of that. And the square root of 16 is 4. So 2 plus 2 root 3 would be 4 times cosine. I need theta. Notice, this is going to be weird. This becomes what do we have there? This was 4. So it's like we have a 1, 2, root 3. Because if you divide all 3 of these things by 2, you get a 1, 2, root 3. So this is 60 degrees. So we got cosine 60 plus I sine 60 is the trigonometric function. Now we're taking the square root, so we're raising that to the 1/2 power. So n equals 2. That means that k equals 0, 1, oh, but not 2. So just those 2 values, because it goes up to n minus 1. So when k equals 0, we've got this set up. We've got 4 to the 1/2 power times cosine of theta over 2, so 60 over 2 plus k is 0 times 360 over 2. And I'm just plugging it into the big formula here. That's 0 times 360 over 2. So let me get a little more space. Square root of 4 is 2. 60 divided by 2 is 30. 0 times anything is 0, so it's 30 degrees. And I happen to know cosine of 30 is root 3 over 2. The sine of 30 is 1/2. Multiply those by 2. 2 times root 3 over 2 is root 3. 2 times 1/2 is 1. So that is one of the roots of 2 plus 2 root 3i. Now let's look at the other one. When k equals 1. And I'm just about out of time, but hopefully this works. 4 to the 1/2 times cosine. I still have 60 over 2, but now we've got 1 times 360 over 2. Notice this is kind of like when we were looking at all of the angles that had a particular sine or cosine, and we had to add 360 to everything to get there. Okay, the square root of 4 is still 2. So this is still 30. 360 over 2 is 180. And now I need to add those two together. 180 plus 30 is 210. A little more space. Cosine of 210 I have from my unit circle is negative root 3 over 2. The sine of 210, again from my unit circle, is negative 1/2. And 2 times both of those is negative root 3. 2 times negative 1/2 is negative 1. And that becomes the other root. So it's a square root. We expect 2 answers. I think I can zoom out and show a bit more. We expect 2 answers from a square root. We got 2 answers from a square root. And it was a matter of plugging into that formula to figure out, plug in the n, plug in the k values, and simplify as much as possible.
Are we ever going to have any that we just can't solve?
I believe we do not have any we cannot solve in this section. I don't recall ever seeing one we couldn't solve in this section.
Okay, thank you.
You're welcome. And I know I'm taking us a couple minutes over, but are there any other questions? This one takes some practice, I know that. Luckily, we've got those formulas and they're well written in the book. The one we just talked about is on page 585. De Moivre's theorem is on page 584. And so write those down, have those next to you, and then kind of practice using them and see what you can just plug in. And trying to remember what we talk about next time. Next time we've got polar coordinates and graphs, but I've extended that into next week. So if we need to talk about this stuff a bit more on Wednesday, we can do that. We've got the time. So go ahead and practice these. Practice these between now and Wednesday, and on Wednesday, if you've got questions, we can go over those and get some more practice in. Our next test is still 2 weeks away. It's not next week, but the following. I think we've got plenty of time to cover all of the material and still get some practice in. And then actually, after that test, we have a week of review and then the final. So we're doing okay. And like I say, we're out of time, so if you want to go, go ahead. If you want to stick around and ask a question or two, you can do that. But I hope you have a good day. I know it's a bit to absorb from today, but give it a go and we'll see where we take it from there. I'm going to go ahead and stop recording.